Okay, this is step 4. So we've fitted our neon lines, we've subdivided our spectras into categories, we've fitted those spectras, if we had them, we've fitted secondary peaks, and now we have a variety of different data frames that we've saved to Excel that we're going to want to pull together. So we have the neon line correction model, we have the spectrum fits, and we have the secondary peaks. And we want to pull all of that together so that we correct our data for instrument drift, and we can do things like calculate the molar ratio of different gases. So first job, load in Python things, and then load in these sort of parameters you set back in step 1, saying where your files are, what file types, etc. So to start with, what this function is doing is this is basically taking those files you made in step 3. So if we just remind ourselves what this was. Do you see we've saved weak, medium and strong, as long as you haven't edited those names. It's going to pull all of those together and it is going to give you the merge. So if you had weak, medium and strong, you would now have all of those together in a single data frame. Now, so far, we've only been dealing with the spectra files because this is WITEC and metadata is separate. We are now extracting the metadata files, okay? And now we're going to stitch that metadata in a loop like we did for the neon lines. And that's going to get us useful metadata like the laser power, the number of accumulations we did, the duration, and most importantly, the seconds since midnight. So the time we acquired the spectra, that is going to be key to make our neon line correction model. We're just going to run this. You then need to make sure, like we did for neons, that the metadata file names and the spectra file names match. Specifically that you are managing to get rid of the prefix. So as you see, there's no prefix here, and that's because it has already been removed because I defined it up above. But you might have made a mistake. You're just going to want to check they're the same. So here I'm printing the format of the metadata file, and I'm printing the format of the spectra file, and you can see they have the same format. It's not like one has a prefix or one has a file ending that the other doesn't. So now we're adding this new clean name that we've called file M. We're going to call this file name, and we've appended it to both data frames. This means we can now merge the two data frames. So we're merging the spectrum parameters with the metadata. So you can see you've got your file name, you've got all your spectrum parameters, and then you've got all of your metadata. So now they are all together. If you have secondary phases, now is the time to merge them in. So this is looking for that file we made in step 3b, carbonate peak fits and SO2 peak fits. And if you have them, it is also merging them together based on the file names. Okay, so it's made a data frame, and you might just want to check, you know, like this should have removed the prefix properly if we go up. So it's merging them, but you need to make sure that you've defined the prefix properly. So do you see it says string prefix here? In this case, it's true, and that means it's knowing to get rid of this O2 space before it tries to merge them, because otherwise it wouldn't find the comparison because we've lost that prefix. It doesn't exist in the metadata the same. Okay, if you have SO2, you might want to calculate the molar ratio, and this is following the methodology of Burke. So basically takes the peak area of SO2, the peak area of diode 1, the peak area of diode 2, and then you need to give it things like your laser wavelength, a temperature, you need to give it a spectral efficiency for SO2 and CO2, and various other parameters. These are from the Burke paper. Charlotte's coded this up, and this is going to give you an approximate estimate of the molar ratio. So this will only do it if it has that column heading. If you didn't fit SO2, you just run this and nothing would happen. Okay, so what's next? We've merged our spectrum with our metadata, and we have merged in our secondary peaks. These next steps will be really dependent on your instrument. If you're using data from UC Berkeley, which is what we've used here, we've made a function which does all of the next steps sort of automatically. So what we need to do now is we need to take that splitting, that's the distance between the peaks. We need to correct it for instrument drift, and we are using the neon correction model here that was saved in step 1. And that's basically going to use the timestamp from this merged data frame, that's seconds since midnight, and it's going to take the value of the neon correction model that you've saved at that time with the uncertainty. It is also going to basically propagate all the sources of uncertainty. So the main sources of uncertainty now are the peak fitting itself, so giving the position of the peaks, that's used to calculate the splitting. There's the uncertainty in the neon correction model, and that's shown by that graph here. And then finally, there's uncertainty in the densimeter itself, and we have to work out what that is, again, from making a model a bit like this, but instead plotting splitting against however we use to calibrate our instrument. And we're going to want to define a confidence interval. So here we are defining a confidence interval of 0.67, and that means all of the errors that we calculate are going to be 1 sigma errors. So what does this function do? It takes the splitting, it applies the neon correction model, and it then calculates a corrected splitting, and it uses that to calculate a density using our instrument-specific densimeter we developed here. So that is this value. This is your preferred density. It also gives you the error on that density, and that is a combination of the peak fitting error, the neon model, and the densimeter. It's going to split that up, so you can see the contribution of this corrected splitting, so that's the combination of the neon and the peak fit is here, and the error from the densimeter is here. And then you can see there's lots of other parameters. This is the corrected splitting. This is the error on the corrected splitting. This is the contribution of the error from neon, the contribution of the error from the peak fit. And then you have all of the other parameters that you might want. What's the final step? We need to save the data frame. So what this is going to do is it's going to save an Excel file. And it hasn't run. So we're going to run that. And this is basically saving a file which is called ramen session of the 20th of September. So this is the day I did the ramen. And then it's giving it the name. So I fitted this data on the 13th of October, 2023. So that's saved. You can open that up, do whatever you want with it. It's literally that data frame we just looked at. We might want to visualize the errors. So that's what this plot here is doing. So what we're plotting here now is corrected splitting and the density. So you can see the error on the corrected splitting and the error on the density. You'll notice the errors are much, much bigger at low densities. That's really pushing the detection limit of Raman spectroscopy. We might want to work out what's the best way to improve our error. So there's those 3 sources of error. The first one we're going to look at is the neon correction factor. So obviously this isn't perfect. There's some noise on how this correction model is working. And we can see that that's contributing between 1 and 14% of the total error. So it is a source of error, but it's not a major source of error. We can then look at the percentage error from the corrected splitting error. So that's your neon line model and your peak fit. And then also the error from the densimeter, and then how they add up to give the overall error. So what you see is that for the lowest densities, we have very, very big errors. And then as we cut down to these higher densities, the errors get smaller and smaller. And what you can see in general is that the densimeter error is pretty consistent. And then there's a lot more variation in the neon and the peak fit errors, respectively. You can also look at the absolute uncertainty, and you can actually see that it's actually pretty constant with densities. This is why the percentage error gets much larger at smaller things. Say you're using a different ramen and a different calibration. At this point, I would really encourage you to reach out to us. We can make a function for your setup that does all of this error propagation properly. Otherwise, you could just save the data frame at this point, this data frame combo secondary phase, and you could apply whatever calculations you normally do to calculate the density, whatever you would prefer. A couple more things we've added in. Let's say these are fluid inclusions. Let's just quickly calculate pressures. This isn't going to be our final published pressures, but it's something to have an idea. So we're going to guess a temperature, which applies to our entire system. We would obviously refine this with microprobe analyses. And we're going to feed in the CO2 density and say we want to use the Stirner and Pitzer equation instead, for example. We could also use the Spann and Wagner, doesn't matter. And then we're going to convert pressure to depth. So here we're just going to use a crustal density profile of 2,300 kilogram per meter cubed. That would apply in the upper crust in Hawaii, for example. And you can see for your day's data, this is the approximate pressure and depth. Now, if these are melt inclusion vapor bubbles, you're obviously not going to want to do this, but this is a good first go.